Good morning, good afternoon, good evening. Welcome everyone to the Friday HSM Hangout. Today we have a special guest within Autodesk that we're very excited to share with everyone. Mike Matera. He is part of our learning, or he is our learning content developer. Mike, maybe you can introduce yourself and what you're doing here with the HSM group at Autodesk.
Yes, Matt, I'd be happy to. Well, thanks everyone for attending. Let me tell you a little bit about myself. I've been around CNC machines or machines in general since I was 17. And as you can see from my picture, that's probably been quite a while. I've been doing applications for machine tool companies, and I've done sales, was a sales manager for a territory for CAD/CAM software as well as machine tools. I had my own business for a while where I produced video training content for a number of different CAM software companies. And I taught at a few community colleges. And today, we're going to be talking about some of the basics of G-code. And it's not going to be enough that you're all going to become G-code programmers overnight, but it will give you enough so that when you look at a program, you'll just have a better understanding of what's there, so that if you have to debug something, or if you're having trouble with the post processor, you can, possibly figure out what's wrong so that we can help you maybe fix that post. That's what we'll be doing.
That's fantastic. And to touch on that a little more, Mike, for the individuals that have followed us for the last couple of weeks, or have found our videos on YouTube, we hosted our CAM Summit at Pier 9 about 3 weeks ago. And this course that Mike had given to the audience there was a big hit, so that's why we had asked Mike to join us here today to present this same content. So before we get started, we wanted to get a poll of the audience here, and we're going to start out with something very relatable to today's topic. How familiar are you with G-code programming? So please submit your answers here. If there's something that you don't feel is applicable, please put it in the chat window. We've got a very small percentage that have voted so far, so please put your votes in here. This will help Mike understand where this conversation needs to be driven.
So while people are doing that, maybe a quick comment here. This is Al Wutmo, the product manager. These questions are super helpful to us, both for Matt and Wayne as they're organizing the webinar. But it's maybe also interesting for you to know that I see partners on our call today from different partners that sell and support the products. I see one of our developers, Aurelia from Copenhagen, who works on the kernel, is on the call today. Matt Nichols is on the call. Many other Autodesk staff are here and standing by to answer questions and really engage with you. So we certainly appreciate the responses.
Yeah, thanks for chiming in on that, Al. So I'm going to close this up. Let's share the results. We do have a pretty even spread here. So a few people can only spell CNC, about 20% of the group actually. So actually a pretty big portion of the group here, what is that, 36% that think it's either Voodoo Magic or can spell CNC. So I think there's a lot of opportunity here for the audience to learn something.
I think that our CAM software is so good they don't have to worry about it, right?
That's true. That's the whole point of what we do, isn't it? We have CAM software so that we don't have to know the G-code, but it is always nice to be able to have some basic understanding. And from what I can see on these numbers, it looks like we have a lot of the right people here for the presentation we're going to be doing today.
Absolutely. So, a couple other things we like to ask every week. Have you been to Autodesk University? We want to keep on bringing this up because, CAM and HSM is becoming more and more a critical part of Autodesk, and we're going to be a lot more present at Autodesk University. We want to make sure that our community is aware of it, and the community is well represented at Autodesk University when classes are beginning to be selected and rolled out. Okay, I'm going to share this. So looks like we're getting a bigger percentage that's been there or interested in going there. So that's always good to see. If you're too busy making chips fly, I think in previous weeks we've showed you where you can receive that content, digital recordings of that at au.autodesk.com. So please continue to watch those videos, and if you haven't seen them, au.autodesk.com, you can have access to a lot of the content that was presented at Autodesk University.
And then how do I get there? I think it's worth bringing up. Time is, AU is still a ways away. It's late in the year, but fairly soon we'll start the process of dialing in who presents, and we look to our users to present, and that will actually cover much of your cost of coming. So that's one way to get there. The other way is the contest we run. We ran one at the end of last quarter, and I hear Curtis wants to run another one coming up, and I'd suspect similar prizes. So keep an eye out for some of those less expensive ways to get to Autodesk University.
Awesome. Thanks, Al. So, we'll just ask one more question here before we let Mike, take this away. But what is most likely to drive the growth of your business? I think we've updated this a little bit. And we ask this every week, that for the developers, for the audience here, for the whole internal Autodesk team, this is very helpful for us to understand where you need more content to help support your business, as well as where the developers need to be allocating their time, with the future of the products. We're about 50% voted. Let's see a little more audience participation on this. I think this is very important with the audience that we have in the background here to provide your feedback, especially on this question. Okay, I'm going to close this up. Share. So it looks like a much higher percentage on the 2 to 3 axis milling. So we might have a lot of new members joining us today. It seems a little different than we've seen in the past week, doesn't it, Al?
It sounds right for this audience. I mean, we're going to be honest. This is maybe one of the more basic but fundamental concepts, and 2 to 3 axis milling is really where I'd expect to start, along with a basic understanding of G-code. So to Mike's point, it seems like we've got the right crowd here today.
Excellent. Okay. So I think with that, I'm going to hand it over to you, Mike, and let you take this away and enlighten the audience here.
Sounds good. Let's get going.
All right. So you should be the presenter now. So I think you need to share whatever you're going to be sharing. And it looks good.
Can you see my screen? All right. So gave you a little bit about myself. One of the other things I do at Autodesk here is I produce some of the learning content. And I'm also the tooltips guy, so just so you know that. So these are some of the things we're going to be covering in this presentation. I'm not going to read through this whole list because we're going to be going through this whole list, but this should give you a good, warm, fuzzy feeling about G-code by the time everything's all said and done here. So we're going to start with some of the origins of CNC machines or NC machines. And NC machines really came about because of Air Force requirements in the early 50s. Back in the early 50s, there were dozens and dozens of machine tool companies just in the United States alone. But because the Air Force wanted better, faster, higher flying jets, there was a need for more standardization from all those machine tool companies. So the Air Force said, we need to standardize these code formats for all these machines. And it would be nice if that actually resulted in standardization, but you'll find that there's probably a handful of codes that will work pretty much the same in just about any machine. But the principles of how these machines work is always going to be the same. And that's really what we're going to focus on in this. And a little historical thing, the first programming system was called APT, A-P-T, which stands for Automatically Programmed Toolpaths. So historically, you may want to Google that at some point and learn a little bit about some of the early programming systems. So G-code programming. Why alphanumeric codes? Why did they decide that that was the best way to convey information to these machines? Well, it was a simple way to define a motion or a function, or to declare a position. We're all used to X, Y, Z axes on a machine. It was also an easy way to set a value, to select an item, or to switch something on or off. You just have some kind of an alpha letter designation with some kind of a number designating what it's supposed to be. Now, there are only 3 basic types of motion in any machine. You have linear motion as fast as possible, which is called a rapid move. And then you have linear motion at a predefined feed rate, a feed move, or you have circular motion at some predefined feed rate. And you can see in the examples here, we have a dashed line, which is usually used to represent some kind of rapid motion. And here's our feed move. And here we can see our circular motion. But all machines and everything that these machines will do is based on these three basic types of motion. So again, why G-code? Well, one might ask, why does a red light mean stop? We all understand that when we see a red light, it means stop, and a green light means go. You go almost anywhere in the world, and you will find traffic signals that look pretty much like this. So it's something that we were told, and it's something that we understand, and that's pretty much the way G-code works. Somebody decided we're going to use G, and they decided that to represent a rapid move, we're going to use G00. And that is the number 0, not the letter O. Keep that in mind when you're looking at these programs. But I like to think that they picked G0 because it looks so much like go. Go as fast as you can to this XY position. And then we have linear feed, which is a G01. Now again, this is just a way for me to remember it, but when I look at the 1, I look at the 1 and think of it as an arrow, a linear arrow moving along a distance. So G01 is a linear feed move. And then we have circular motion, and there's two types, circular clockwise and circular counterclockwise. So when I look at a G02, I see the single loop for the 2, and I think clockwise. And when I see the double loop for the 3, I think counterclockwise. It's just the way I see it, and it's just something that helps me remember it. I don't think that's why they picked those, but, you know, could be. Who knows? So typical NC code, you're going to have some kind of a alpha and a numeric, and generally you're going to find that a G is going to be used to define some kind of a motion code. It's going to tell it how it's going to get there or what it's going to do when it gets to the point. And then you'll have something to declare a position, normally an X, Y, Z. And then we have the F word or the S word, which is used to describe a feed rate or a spindle speed. So we're setting a value for something. And then we have the T word, which is used to select an item. In this case, we're selecting a tool. And then we have miscellaneous functions. Miscellaneous functions will switch something on or off. And on a CNC machine, there's a lot of things that you might want to switch on or off. Things like coolant, spindles, indexing motion, axis locks. There's a lot of things. So just with the information I've given you so far, you should be able to look at this line of code and get a general idea of what's going on. So we have a G1, which is a linear feed move. We have the XY position that it's going to feed to. We have a feed rate. We're using tool 1, and we have a spindle speed of 500. Now there's an MO3 there. That's a miscellaneous function, and we don't quite know what that is yet. And for most miscellaneous functions, you're going to have to get the actual chart for your particular machine, because these will vary a little bit from machine to machine. But I've created a list here of some of the most common M functions. Now you'll find that these are the M functions that will be most standard, but I can't guarantee that these will be the same on all machines. So in our case, the M3 is a spindle on in a clockwise direction. Next, I want to talk about something called modality. The concept is easy. If it's on, it stays on until you turn it off. So if you have kids at home, you might be familiar with this concept. So your kids will walk through the house, and as they go from room to room, they will turn on light switches, and all the lights will be on. And every room that they go to, the lights will get turned on. And those lights will stay on until you come home from work and walk through those rooms again and turn those lights off. So a light is an example of a modal condition. You turn it on, it stays on until you turn it off. Now, in the case of some of these codes, you can use an additional code to turn off the previous function. So here we have linear, feed, and clockwise and counterclockwise motion. Well, I can't do a circular clockwise move and a linear feed move at the same time. So any one of these codes will overwrite the other one. So if we had a program that looked like this with a G0, which is a rapid move going to X1, Y1, the next line, I wouldn't have to say G0 again because the modal condition is a linear rapid condition. I just have to specify the XY position. Now I can say G1 with an X position, so it's going to do a linear feed to that X. Now on the subsequent lines, I just have to spell out the next Y or X position that I want to move to, and it will continue to move in a linear feed motion. So that's an example of modality. Once a condition is set, it stays active until it's turned off or some other condition overrides it. One great example of modal conditions are canned cycles. Now, canned cycles are great because they incorporate all the motion that you would normally do to complete a common task. In this case, the task is drilling. Now, the normal drilling cycles are G81 through G89, but again, that could vary on a lot of machines. So in the case of basic drilling, you basically would move to the starting point for the location of the hole, you would wrap it to the clearance plane, feed to the depth, and then wrap it back out. So if you were going to count that up, that would be 4 lines of code in your program. Wrap it to the start, move to the clearance, feed to the depth, and wrap it out. So if I had to go to the next location and do that again, I'd have those same 4 lines of code if I didn't have a canned cycle. So you could imagine if you were trying to drill 500 holes, that would be a lot of code. But by specifying the canned cycle, all I have to do is tell it once what I want to do, and it'll continue to do subsequent holes. Now here's an example of a peck drilling cycle where it's taking multiple pecks to get to the final depth. Now you can imagine if I did that all with linear moves, that would be a lot of code just to do one hole. Here's an example of a counterboring cycle where it'll feed to depth, it'll dwell, and then wrap it out. So that's for counterboring or polishing up the bottom of the hole. And here's another one. This is a tapping cycle where it will feed in, reverse the spindle, and then feed out. So this would be used for threading a hole, tapping a hole. So again, it's a modal condition. Once we specify the drilling cycle and the location and what we want the depth to be, all we have to do after that is specify the subsequent locations. So you can see that this would save an awful lot of programming if you had to write this program manually. Now the next thing we have to have an idea of is code groups. Now I mentioned that a G01 will override a G0 or a G2, but there's other codes that are in that same group. So with a G81 drilling cycle, I can override that with a G80 or a G82. I can have any of these codes on a single line, but you can only have one code from each group on a line. So here we have plane selection, we have things like cutter compensation, so I could have one code from each one of these groups on a single line. At the bottom you'll see the work offset codes, G54 through G59, and that extends out on some machines to be G59.001, 002. So you can have extended work offsets. That allows you to shift your 0 to different locations on the workpiece or different locations on the table. All CNC code is not G code, but all machines require the same information. Not all the information is going to look the same, and that's the reason why we have 1,000 post processors in our library. Because every machine builder can take a standard CNC control and make it do whatever he wants. So because of that, we're always going to have little variations from machine manufacturer to machine manufacturer, even when they might be using the same control. So here's an example of the kind of things that we would need to know in order to perform some kind of a CNC task. In this case, the task is creating an arc or a circular move. So we have the green dot, which represents the starting point of the arc. We have the blue arrows, which represent the cutting direction, which could be clockwise or counterclockwise. And then we have the red dot indicating the end point of the arc. So you can see there's 4 different ways to get from the green dot to the red dot. But we narrow that down by giving the control more information. So when I tell it the direction that I want to go, and then if I can tell it the center point of the arc or the radius size, those are also ways to tell it specifically the kind of arc that I want to create. So we have to have that information to do an arc, no matter which control you have. It has to know these basic things. So here's an example of what that code might look like. So the first blue bar up on top shows the code that you would use for a Fanuc control or a Haas control. They're very, very similar in format. So the first one shows an arc that uses an X, a Y, and an I and a J to describe the center. Next to that, it shows an X and a Y and a radius. So it's using the radius, an R plus or R minus, to determine which portion of the arc that it's doing. So that's 2 different ways of doing the exact same arc in the same control. Next is the control that I have, which is an Analam control. Now, Analam was known for their conversational format. So when we look at this, we can see it says arc clockwise. We have the X and Y position. It says arc center. It says, I'm sorry, X center and Y center. So it's pretty obvious what that represents. And then the feed rate. And there's another way of doing it, again, within that same control, where you can say arc clockwise, the X and Y endpoint, and then we specify the radius. And then one of my all-time favorites at the bottom is the Heidenhain control, where there's even more variation on how you can do exactly the same kind of an arc. So they do it with 2 lines. The first line describes the circle center, and the second line describes the circle direction, CW, the X and Y endpoint, and the feed rate. So again, no matter what machine we're programming for, we have to have this basic information. And that's kind of the idea of this presentation. If we understand better what our machine wants, it'll help us if we ever have to modify our program or maybe make some changes to our post processor. These are the same things that someone else would need to know in order to change that post. So post processors, let's talk about that. A post processor is basically a translator. It translates the image of the toolpath on your screen into the language for a specific machine control. So basically you can see our toolpath here on the left, and we can see some code here on the right. It's a standard G-code format. So we have a lot of these different translators because there's a lot of different control types. Now, if you needed to have a post processor made, these are some of the things that anyone would need to know in order to help you create that post. We would need to know the machine manufacturer's name, the model of the machine, the control that's on that machine, and the model of that control. That's going to tell you which post processor you should start with as a base sample. So if you just downloaded Fusion and you just got your first CNC machine, basically you want to find that information and use that to search through our post library and find something that looks like it's going to be close to what you need. And then you're going to use one of our sample test programs. I'm jumping ahead in my list here a little bit. But you'd use the sample test program to create code using that standard post. Some of the other things we need to know is the type of machine, the number of axes, and the axis designations. So is it a vertical mill? This is 4-axis, and the axes are called X, Y, Z, and A. That tells us a lot about which post to use. We would need a list of the G codes specifically for that machine and a list of the M codes for that machine. So now when you take one of our standard posts and our post baseline test program, you can create code and maybe make the changes that you need so that you can send it out to your machine. You'll probably have to make some additional changes at the machine to get it to work specifically for your machine. But once you have that, that's the sample program that we're going to use to help modify your post. We want to make the code look exactly like that. And that's why the sample program should have been successfully run in the machine with no errors. A lot of times when you get a machine, it comes with a programming manual, and they always have some sample programs in the back of that manual. And I have never seen those programs work successfully.
Yeah, I don't
You always have to download something to the machine.
I was just going to say, I don't think you can reiterate this enough. I've seen cases where literally the decals on a machine said X positive is in this direction, and it actually was going the opposite way. So it's crucial that you test on a known small problem before trying to run a big program. And one other quick comment while I'm interrupting you. There's a lot of new users on the call today. You may or may not know, if in the GoToMeeting you'll see a little orange arrow. If you click that, you'll see a section where you can ask questions. Feel free to interject along the way and ask questions of Mike. He's truly an expert and more than open to answer questions if you're struggling with any of these concepts.
Yeah, I hadn't been interrupted by anyone at all, so I was wondering if anyone was actually hearing me.
We're hearing you fine. I think you're A, doing a great job, and B, we've got a lot of new users on the call today, so they may not have known how to engage with the question area.
Good. Well, I hope everyone's sucking it up, because there's some good stuff here that I hope you're finding useful. But yeah, it's really important that you have a sample that you take our benchmark test part, which is in our CAM samples folder, and you use that benchmark to create a program, because now we have a known standard that we can all gauge against. And when you get that program to work successfully in your machine, now we know that this part is supposed to look like this code, and it really helps us to put the whole thing together to get a more refined post processor. So that's pretty much all I have. I'm open to take any questions that anyone has.
Great. So now that we're in the question period, I'm going to call out a couple things. First and foremost, any G-code related question, feel free to try and stump the team. We've got Mike and Angelo on that are both CNC experts. If there's a post-related question, I noticed Renee Fonseca slipped in from Copenhagen. We've got Matt Nichols on the line, so definitely some post experts on the call today. So feel free to ask some questions. I do see some questions regarding availability of both the deck and a video. There's actually a live video of Mike doing this presentation in person uploaded already. We'll also upload this presentation, and I'm sure, Mike, you're open to sharing the deck so others can maybe use it to teach in their respective locations.
Absolutely, not a problem. We'll make that available. Well, you know, G-code, it may look like voodoo to some of you. It's not really that big of a mystery. If you actually take some of those G-code charts from the back of the programming manual, and when you're looking through some of the output that you get from your HSM or your Fusion, one of the ways that I learned was actually I was running a machine, and I would analyze each line as I was running it step by step so that I knew what that line was going to do. Eventually I got to the point where I could look at that, compare it to the print, and occasionally I'd find something wrong, and I'd go into the programmers and say, this line is wrong. Eventually we got to the point where I'd go in and say, this line is wrong, it should be this, and at that point they handed me a set of keys and said, great, you're the lead man, we're sending everybody to you now to get their programs fixed. So when you step up, good things happen. So no questions, huh?
No, I'm seeing questions roll in here. You're not off the hook, Mike. Jonathan's got a great question. What are the most common problems that happen in a Fusion post-processor? I guess there's two answers to that. The first one is when we know the common problems, we try and bake those into switches. So I guess if I had a solid answer for that, then we're not doing our job. But
yeah, that is a really good question.
Maybe
one of the things,
comments on that.
One of the things that I always find is it's always the something in the tool change sequence. Maybe their machine can't have the coolant turn on the same line with the tool, or maybe they want the coolant to turn on after it reaches the first hole location. Little things like that in either the startup or in the tool change, or as it's ending an operation before it goes to a tool change. Those are usually the areas that have to be modified, because as I said, G-code is pretty standard. You saw the FNUC format and the Haas format were pretty much identical. So if you have a pretty plain vanilla G-code control, how we do the arcs and things like that will rarely be the problem. It'll always be something in the way the tool change sequence works, or the startup of the file, or the end of the file. Matt, was there something you wanted to add to that?
I just pulled up my screen because I think it's worth showing some of the concepts you did in Fusion, and we had a little bit of time. Mike had mentioned using a standard part with some very basic toolpath to validate your code. What I'm showing right now is the post-processor area in the samples folder. I'm just going to go back a couple folders to see how I got there. So we're scrolling down to the bottom in Fusion 360. We see CAM samples. As a shout out for Mike, there's actually a link here to the documentation that Mike works on, so you can take a look at that. But if I go into CAM samples, for many of you learning the product, again, a shout out for all the sample files. You can see ways different parts have been programmed and reverse engineer things, which I think is very helpful for many machinists, your tradespeople that learned on the job, and this is a great way to reverse engineer things. But inside of here, there's a post-processor folder, and here you're going to find some benchmark parts that test all of the functionality of the software, the basic motion, though, as Mike had said, for water jet, for milling, and for things of that nature. So if I take a look at something like I want to verify my drilling cycles, which Mike had talked about. We can look at a chip breaking cycle. We have two simple holes. I can select that operation. I can select post-process, pick a post-processor, and start to validate whether or not it's going to work on my machine. So I'm going to pick the Haas post. I'll give it a number, and I'll hit post-process. There's a couple of things I want to show here. In regards to what the post-processor can do. I probably should have prepared for a demo so that I'd know that brackets was already installed.
And brackets is just the NC editor, just so
yeah,
you're all familiar.
Just a viewer to see the code. I do also see a question around DXFs. Jeff, I'm sure you're aware that there is a DXF post that outputs based on color. Jeff is asking about a post based on layers. It's a great question, and I'll let one of the experts on the call here dive into that. So this is actually interesting. What I have here, and I purposely selected the POS post with chip breaking. I'm actually seeing this drilling cycle expanded out. You may see that. There's instances where the post processor actually understands what the machine can and can't do. In this case, our software has an ability to do incremental retracts. It'll peck, 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 and then come out. That wasn't one of the CAN cycles Mike talked about because it's not a common CAN cycle. If I come into this operation and I edit it, sorry, it's on my second screen here. I'll drag it over. And I come to the cycle, you'll see that I have a accumulated peck depth. That means every 5 millimeters we're going to come all the way out of the hole. So if I'm just going to increase that to something like 500, so it's more than it would produce an incremental retract. And then I'm going to post-process again. And now I have a chip breaking cycle. So I wanted everybody to see that because sometimes you look and wonder, why am I not using a CAN cycle? Well, the post processor is actually intelligent enough to know that we created a cycle that a CAN cycle didn't support, so we went and automatically expanded the cycle. But then when we put a set of options in that didn't require the incremental retract, something that currently HOS doesn't support, we could then return to using a CAN cycle. So I think it's that's maybe a helpful trick. The other little trick I'll show here quickly is if you're trying to do some multi-axis programming or 4-axis programming, you'll see some very simple moves that do just a simple rotation so that you can look at a very short piece of code and identify whether or not that's happening. I see some questions around coolant. So again, with a very simple cycle, test the coolant code. So hopefully those are some nice little tricks for how you can leverage these parts to validate a post-processor.
If I could expand on what Al brought up about the peck drilling. So again, this is the reason you want to have a good CAM system, is because it gives you capabilities far in advance of what your machine would normally do. So we have a more advanced pecking capability than that particular control might have. But so basically we're expanding on the capabilities of what the machine could normally do.
Okay, I see some other questions here. Let's just take a look and read through them. Some people asking for a G-code simulator to practice with. There's the number of options out in the market that is going to be largely driven by budget. So that's a difficult question, but maybe some of the other experts on the line, let's just jump in that question and try and answer it.
I used to use one called NC Plot. There used to be a free version of NC Plot, which just did basic milling code, but you can upgrade it, and I don't remember how much it costs, but it'll do more advanced code, and it actually reads the NC code and plots it on the screen. So NC Plot is one that I'm familiar with.
So Neil had a great question, which sort of ties into this same thing. He wanted me to show how we see the toolpath, and I'm actually going to show two tricks here that many people probably don't know. The first is if we expand out an operation, you're going to see the tool, and you're also going to see this little 110 bytes. That's telling me how big the internal representation of the toolpath is. Just looking at that size is actually very helpful when you're playing with smoothing options to try and reduce the size of your program. So that's the first trick. The second trick came from Neil's question showing what the toolpath is. So if I right-click and say View Toolpath, I'm going to see the internal data that the CAM system has that ultimately it passes to the post processor. I need to make a line move, and I'm rapiding. I need to make another line move, and I'm rapiding. I'm then making a linear move. I'm now doing a finish cut. So these are the simple types of motion that Mike described earlier in the presentation that the post-processor then converts into the language that your particular machine needs. So thanks for drawing attention to that, Neil. So this question is starting to go off in a different direction, but Timothy is asking for a good resource on writing expressions. For those that don't know what the expression is, if I look at this face milling operation and I were to change the tool, so I'm going to just select a different tool. And again, I have dual monitors. If any of you don't have dual monitors, you should. I don't know how you do engineering software without it. But anyway, I'm going to change the tool, and you'll see immediately I have a slightly different step over. And that is driven, well, maybe it wasn't in this case because this demo is changed. So this particular file locked in a step over. So let's do a new facing operation. So I'll do a new facing operation, and I have a tight step over, and then I'm going to edit this operation, and I'll select a larger tool, and instantly I have a larger step over. That was driven by an equation, and obviously in that last operation the equation was changed. So the equation is over here on the step over. If I right click, I can say, sorry, expression, edit expression, and we can see this bit of math that's deciding how we calculate that particular step over. In this case, it's looking at the maximum value between the tool diameter minus the quarter radius, or 95% of the tool diameter. What's the biggest of the two? What's the purpose of that? Well, if you use a ball nose end mill, you want to still have a solvable solution. So this is a long answer to your question. The answer to the question is this is all JavaScript. So looking at any documentation on JavaScript is a great place to start. The next bit you need to know when you're writing equations is how do I find out what these different parameter names are? And the trick to that is when I hover over a tooltip, there's a slight delay. Let's hold Shift, and John Saunders just caused a little bit of stir on this one. I appreciate him doing it in one of his videos. If you're not watching it, you should. He was having trouble with this, but hold Shift and then come over the field. You're going to have to wait a few seconds to see the tooltip, and then on that tooltip you have a different tooltip that shows the parameter name. In this case, we can see the pass angle. Do pay attention to that lowercase p and the uppercase a. That does matter. Okay, hopefully I didn't spend too long on that question.
I've got a question here I'm going to field from Jonathan. Why does it sometimes pick linear moves to create a curve and sometimes an arc movement, G1 instead of G2? And that kind of depends on what type of curve you're cutting. So if you're cutting something that's more of a spline curve, then it may not be represented as a true arc. So then Fusion or HSM will break that up into a series of linear moves to create the same motion within whatever tolerance you have it set to. But something that you can do to clean that up a little bit, and Al's going there right now, is the smoothing function. So if you are cutting something that's more of a spline curve, the smoothing will filter that back into arcs for you. It'll give you a smoother contour and a much smaller program size. So that's something for you to look into, Jonathan.
And so there's two more things I'm going to add to that. First, why is it called smoothing? Oftentimes people say you should call it arc fitting. The fundamental reason it's called smoothing is smoothing will also use lines to best fit across a series of tool paths. So it can use either lines or arcs to reduce the code size, and that comes back to sort of looking at this code size value to see what's happening. The other thing you do need to be very aware of, and this will play a part, is your post-processor. So if we look at any post-processor, we've got this series of defaults that are called built-in defaults. The top one is allow helical moves, yes or no. We're defaulting to yes. Some machines don't allow a helical move, which is an arc that's actually going down in Z at the same time. So we may have had that arc in the internal representation of the toolpath, but then the machine doesn't support it. So now we're going to turn it back into a series of lines at the built-in tolerance. So it is important to know that even if it's an arc inside of the CAM system, and maybe a good example might be this helical bore. I have some arc moves, but then I may have a machine that doesn't support that. So we're going to need to linearize it. And just maybe a quick tip, if you're trying to find it, if your machine will do it, it's actually pretty scary. I've seen some machines do it. Many won't even give you an error. It'll actually just do an arc and then drop in Z by whatever it was supposed to drop, and then an arc and drop in Z again. So you may not get an error. You may just get some real funny motion on your machine. So it's nice to test with a very aggressive helix. I have Renee from Copenhagen correcting me. Feel free to unmute and add anything that I may have said that's wrong. I'm far from perfect.
Yeah, just one thing is that often we would output arcs that are not in the primary planes, G17, G18, and G19, and those arcs would have to be linearized to run on the specific CNCs. So we try to generate tangential motion. So if you run a parallel in 45 degrees, you would definitely get arcs that need to be linearized if the machine doesn't support it.
Excellent add. Hopefully that makes sense to everybody. So even if it's an arc that's in a plane, not necessarily a helix, but some machines don't support arcs that are in other planes. Thank you, Renee. And again, I think this kind of circles back to the first thing. So thanks for speaking up, Renee. The value of these live Hangouts. They truly are supposed to be an interactive experience, and hopefully you all are enjoying that. This presentation is something that we actually posted a video to a week ago on what Mike did, but really the value of these Hangouts is to allow you guys to engage. So I'm glad to see everybody engaging and other Autodeskers jumping in here too. It's awesome.
Yeah, when we were talking about those code groups, actually that plane selection that he just mentioned earlier, so G17 is the XY plane, G18 is the YZ, and G19 is the ZX plane. So that tells it which plane you're doing your contouring in. So normally we think of doing contouring in XY, but you don't have to just contour in XY. So if you pick a different plane, we can swing an arc in Y and Z or X and Z. But if you think of a circle that's tilted at an angle, that doesn't actually conform to any plane. And that's, again, where we'd have to output it as individual linear moves.
So Kevin asked a question, how do you get all the parameter names? One way to do it is to use the dump post processor. Those parameter names are the same there. So that's one way you can do it. The dump post processor basically exposes all of the information that the post has. There's also another question from Mike here. What's the difference between Fusion and HSM? The correct answer is Fusion is a less capable version of HSM. That is a complete joke. The underlying technology is the same across all three of the HSM CAM products, whether that be in SolidWorks, in Fusion, or in Inventor. Now there are some differences. There's some cases of things that we did in HSM Works where when we were given a second opportunity to do it again, we chose that we wanted to take a different path. So there are some things in HSM Works like machine simulation and wrapping of 3-axis toolpaths where we made a conscious decision to not port over as is, but take a slightly different approach on how we do it. So you've seen that in how we've released wrapping of 2-axis strategies instead in Fusion, and that has not made its way back into HSM Works. So there are some some cases where we're sort of taking a slightly different approach given the opportunity, but more or less the underlying toolpath, the quality of the toolpath, the speed of the calculation, all of those things are the same across everything. Hopefully that was helpful and answers your question. There's some questions around hand programming. Mike, the question is for you around some tips and tricks for hand programming.
Yeah, I was just reading that one. So let me read it out loud. Are there some resources Mike might recommend for simplifying hand programming arcs for mill and lathe to better understand it? If you're doing it by hand, the best thing I could recommend is a piece of graph paper. If you're laying it out by hand that way, it's really just a good idea to visualize it as much as you can. I can't think of any specific tools. Once you know the rules for creating arcs, the rules are the rules. It's just a question of visualizing, where things go.
So there's one thing before we wrap things up that I think I want to address. Maybe I'll answer this quick question too. There's a question around making a post-processor edit. We can't let one of these webinars go by without pointing people towards the forums. So I highly suggest you go join Seth and Neil and Rob and the other power users on the forums. There's a specific post-processor forum. If you ask your post-processor editing question there, I'd expect one of our guys or one of the power users to jump in and help you through it. So please do that. The last thing that I want to address, and I personally see a change happening in the industry. Mike had suggested that what the machines need are just the guidance codes. I think you start to see interesting things happen with Haas. I think they're a great example of that, where they've introduced M130. We can actually embed images into the G-code so the machine can display setup information. And the extension I would make on everything you presented, and you presented everything perfectly, Mike, is we're starting to see machines accept more information to help give the operator some heads-up information on what's going on. So to me, it's exciting to see that machine vendors are thinking about accepting and making use of information beyond just the motion codes. With that, I think it's probably getting to the top of the hour. Appreciate everybody that stuck around. Why don't we pass it over to you, Matt, to wrap things up. We'll get this posted. We'll get the presentation posted so some of you can teach in your classes. I know there's some students, but Matt, what else do you have to add here?
Yeah, I mean, I just want to echo a couple points that you made. Especially with attending live, as you said, this content was really posted a week ago on the webinar, but look how much interaction that we've had from the audience and from the background Autodesk team that makes all this happen. I think having that direct feedback for an hour a week is really something special that you don't see in a lot of other places or even with other products at Autodesk. So we really encourage everyone to join these weekly hangouts live. Invite your friends, invite others that you think might benefit from that. I can't express that enough. People always ask me where the recordings are available. They are available on YouTube, but again, we do appreciate the interaction live, and it's a great opportunity for you to get direct feedback to the background team here at Autodesk. I'll take over control here for one more second before we end it.
Matt,
Yep.
if I can make a shameless plug on the Fast Track, encourage everybody to go sign up for the HSM Fast Track. We're doing events monthly in local HFOs and at some of our customer sites where you can get hands-on with Fusion 360 and HSM products. We send out various events that are going on around, so sign up for that. You also get Pluralsight training, so just something for you guys to be aware of.
And I will add to that point, the voice you're hearing is Garen Gardner. Garen is responsible for a lot of our partnerships and our strategy there. So that strategy is twofold. One, the fast tracks, but also the relationship with machine tool vendors. So if you're joining us and you work for a machine tool vendor, you want us to have a better out-of-the-box experience for your machines, Garen Gardner's a guy to start that conversation with. So thanks for jumping in there, Garen.
Yeah, no problem.
Yeah, Garen, I'm really glad you bring that up. And I talk to customers all the time, and they're wanting to know how we can get up and running with HSM quickly, something new to them. And these fast track programs are doing a really good job. The on-site ones as well as the online fast track learning path that we've received really good feedback with. So the last couple of things I wanted to share here, a lot of the things we've referenced on this Hangout. AU, Autodesk University is the event. Here's the dates down here, November 14 through 16 this year. You'll see more and more CAM and HSM content be a part of this event. So, stay tuned. As I mentioned, you can go to the online learning here and watch the recordings from last year on demand. Some other things, the HSM community that was, referenced many times by all the individuals on the call here. This is a great place to, engage with the development team, the application engineers, the level 70 users that we have on, like Neil and Rob. And, there's other forums for Fusion as well. So in the Fusion forums, there's a CAM forum specific here. A lot of the people that are on the call are the ones that are posting these stickies and are really involved. So want to encourage everyone to spend more time there. You'll be getting a lot of the same types of responses we're getting live here, but, not on Fridays. So other times throughout the week. Post-processor adjustments, there's a nice post in that forum where you can find help. There's been a lot of questions on that recently. The HSM YouTube channel, so all the recordings are posted here. There's also a lot of quick tips and great content. So, we encourage everyone just to follow this. When new videos get posted, you will get notifications about that content. And then the last thing is the Autodesk Knowledge Network. There's, I think, over 1,600 articles focused just on HSM. So if you go to the top search here, HSM is one of the fields in here. Maybe not but if you search HSM in the search bar here, there's tons of great content. If you're, working in your shop late at night, there's something that you can't figure out. There's likely information in here on the Autodesk Knowledge Network that'll get you to solve your problem on the spot there. So we encourage everyone to use these resources. These were internal application engineer resources for Autodesk, and now they're available to the general public because it was such a useful tool. So, these are the resources that we bring up every week, but we encourage everyone really leverage these things. They're free for our community of users, and they'll make your life much, much easier. So I think with that, we'll end our Friday Hangout this week, and thank you everyone for joining. We look forward to talking to you again next week.
Thank you for attending, everyone.
Thanks, Mike.